Welcome to part 4 of formation of differential equations. This part 4 consists of a mixture of different kinds of functions. As you can see, we have an exponential and trigonometric, which is going to be a common mixture that you will encounter when you're dealing with differential equations governing different systems. So we have an exponential and mixed with a trigonometric. So let's obtain the differential equation for this kind of system. Now it's still going to follow the same procedure. Now, as you can see, our y is equal to exponential 2t open brackets a cos 5t plus b sine 5t. So what do you do in this scenario? You differentiate 2 times, right? Okay, very good. But let's see how complicated this one can get. So y is exponential 2t into a cos 5t plus b sine 5t. So this is our equation 1. Now let's obtain y prime. So to obtain y prime, now there's something that you should not do. Please, when you're given this kind of equation, do not expand. It's going to be very difficult if you try to expand. Is that okay? I would rather you simplify it like this, or if this kind of equation is already given to you in an expanded form, try to put it in this form. The expanded form will be a exponential 2t cos 5t plus b exponential 2t sine 5t. That's the expanded form, but you should factor out the exponential term and you should solve it like this. Notice that the cos and the sine have both the same frequency parameter, which is 5 in this case. Is that okay? So this is how we are going to solve this problem for simplicity at least. Now back to obtaining y prime. To obtain y prime, you need to differentiate using what product rule. Okay, differentiating by parts. So I'm going to hold in this first case exponential 2t, and I'm going to differentiate the brackets. So in differentiating the brackets, we'll have minus 5a sine 5t, then plus 5b cos 5t. Is that okay? So that is, I held exponential 2t and I differentiated the brackets. So this time around, I'm going to differentiate exponential 2t, which will give me 2 exponential 2t. Then I'm going to rewrite the brackets, which in this case is a cos 5t plus b sine 5t. Is that okay? So if you observe very carefully, your y prime is exponential 2t into this particular junks here sine 5t plus 5b cos 5t, then plus 2y. So this is where I want us to stop for equation 2, which is our y prime. So if you don't do it like this, if you don't quickly figure out that this whole term corresponds to y, bro or sis, man, you're going to keep solving. Like this one is long, but you need to know how to like capture things like this. So let's go for y prime prime. So y prime prime, we are still going to differentiate by parts or using product rule. So I'm going to hold this term exponential 2t, and I'm going to differentiate the brackets. Take note, I'll get negative 25a cos 5t, then differentiating this one, I'll get negative 25b sine 5t. Okay, that's what I get by differentiating the brackets. Then I'll now differentiate exponential 2t. Remember, we held exponential 2t, we differentiate the brackets. So what we are going to do next is we are going to differentiate exponential 2t and we rewrite the bracket. So differentiating exponential 2t, you get 2 exponential 2t, and you rewrite the brackets minus 5a sine 5t plus 5b cos 5t. Then when you now differentiate this 2y, you get 2y prime. Is that okay? So now you agree with me that if we restructure our y prime prime, I can see some repetitive parameters. I'll factor out minus 25. You will now see exponential 2t, then into a cos 5t plus b sine 5t, then plus 2 exponential 2t, then we now have minus 5a sine 5t plus 5b cos 5t plus 2y prime. So do you now agree with me that this particular term here can now be replaced with y from equation 1? Okay, so y prime prime is equal to minus 25y plus 2. Now this particular term here, if you look at it carefully, if you go back to your equation 2, it is the same term that is actually playing. So assuming I make this term the subject of the formula, you agree with me that the whole of this exponential into minus 5a sine 5t plus 5b cos 5t is equal to y prime minus 2y. Okay, making it the subject of the formula together. So you have 2 into y prime minus 2y. Okay, are we together? Then plus 2y prime. Okay, so let me assume I break it here and I keep solving. So this implies that we are going to have our y prime prime is equal to minus 25y, all right, and plus 2y prime minus 4y plus 2y prime. So if we arrange this together on the left hand side, we'll have y prime prime minus 4y prime then plus 29y is equal to 0. So this is the differential equation governing the system: y prime prime minus 4y prime plus 29y equal to 0. So stay tuned, I'll still show you another method to solve this particular problem. So it's using auxiliary equations like we treated in one of the parts, that is in part 1 or 2 thereabout. So let's see if we'll get the same answer. Now we want to look at another method of solving problems like this, okay, using auxiliary equations. So if you want to use the auxiliary equation approach for solving this particular problem, now remember that the general form of expressing our auxiliary equation is going to be something like this: m minus m1, okay, then m minus m2 equal to 0. Okay, so where m1 and m2 are the roots of the auxiliary equation. Now why do I just have m1 and m2? I have m1 and m2 because I'm dealing with two arbitrary constants. Are you with me? So I'm just dealing with two arbitrary constants. If I was dealing with three arbitrary constants, then I'm going to have an m3, and definitely you have your m1, your m minus m1 brackets, then m minus m2 bracket, then m minus m3 bracket, and equal to 0, and so on and so forth. So for two arbitrary constants a and b, your auxiliary equation will be stated like this, where m1 and m2 are the roots of what? The auxiliary equation. Now let's just call this one equation star, or equation 1 for instance. So what exactly is m1 and m2 based on this particular equation? So this is going to be a complex value. So m1 is a complex value. The real part is 2 and the imaginary part is 5. The imaginary part is the angular frequency in this particular sine and cosine terms. So for m2 is just the conjugate of what? m1 and m2 are the same in this kind of scenario, so m2 is the conjugate, so you still have 2 minus j5. Okay, so this is the conjugate value, and let's see how we are going to find our answer by opening the brackets now. So we have m minus 2 plus j5, okay, and m minus 2 minus j5 equal to 0. Okay, so you want to expand it like this. Then you have m squared, this times this. So we'll now do this times this is minus m into 2 minus j5. Then this times this is minus m into 2 plus j5. And finally this times this is plus the conjugate values, the product of the conjugate, 2 plus j5 multiplied by 2 minus j5. Okay, so I'm just going to transfer the working up here. So we are going to have m squared in this case, then I now have minus 2m minus j5m. We have minus 2m. We now have the first one is plus j5m, because minus 2m, and minus times minus is plus. Now I have minus 2m and minus j5m. Okay, then where j is the imaginary value, I hope you still remember, then plus. So when we multiply conjugate values, it's actually like difference of two squares. Okay, when you multiply conjugate values, it's not difference of two squares this time around, it's addition of two squares. So it's just as good as you saying 2 squared plus 5 squared. Okay, so and this is equal to 0. Are we together? So whenever you multiply conjugate values, just know that you are actually doing the summation of two squares. Okay, so there is actually a difference between difference of two squares and summation of two squares. The summation of two squares comes about when you multiply complex conjugates. Okay, when you multiply complex conjugates, you get the summation of two squares. But when you multiply ordinary linear factors, okay, that are actually opposite in the sign in between them, you get difference of two squares. But the multiplication of complex conjugates gives us summation of two squares. So we now have m squared, and collecting the like terms, you get minus 4m, then plus j5m, and minus j5m cancels out. We have did I miss something? Plus 4 plus 25 is 29, and this gives me 0. Okay, so remember we now called our m squared corresponding to y prime prime, and we called our 4m corresponding to 4 y prime, and we called our 29, which is 29 times 1, and it's still the same thing as 29y, which is equal to 0. So in transferring your auxiliary equation to your differential equation, every m squared represents a y prime prime, every m represents a y prime, and every invincible one represents a y. So you can see now that at this point, this corresponds to what we got initially. This is what we got initially from the first case. So when we used the normal method, simultaneous equation method, so whether you're using the auxiliary equation approach or you use the normal elimination method and substitution method, you should, if you solve correctly, you should arrive at the same answer. So this brings us to the end of part 4 on formation of differential equations. So we are going to be looking at linear differential equations. From the next class, we'll learn how to approach linear differential equations. And okay, before we do linear differential equations, I think we should look at different methods of solving differential equations. Okay, so stay tuned and let's see how we do on the next class. Don't forget to like and subscribe and hit the notification button to stay updated on post. Now, if there's any question, if there is any confusion, you could drop it in the comment section and I'll attend to it as soon as I see. So thank you very much.